Hey everyone. Today it's March 9th. It's 9:30 a.m. I hope you guys are having a good start to your day. Um, and Abel. Today is the last Monday before spring break. I'm like 99.99% sure on that. I'm gonna look at my calendar just to affirm that or confirm that. Yeah. Yep. So a week from today, we will not meet. A week from Wednesday, we will not meet. And actually, this Wednesday, Wednesday the 11th of March, I'm going to have a pre-recorded lecture for you guys. So we'll not have our live Zoom meeting. I'll have my office hours. I'll join the Zoom meeting. But I wanted to give you guys a little bit of flexibility in the event that you're like, if I could get to my spring break destination 3 days earlier, that'd be awesome. Um, so I'm going to um, have a pre-recorded lecture in place of Wednesday. Okay, so I don't want this to be confusing. Wednesday will be pre-recorded. I'll have that up before our class actually meets. And in addition to that, though, I will have my office hours. And if there's a time on Wednesday that you want to meet, I'd be glad to. Um, then the last thing, kind of an announcement. Um, we don't have any poll questions today, and I kind of put a pause on them because I'm a little bit behind on my grading and poll questions and discussions. So I need to get that sorted out before I'm going to do any more poll questions. You'll have a discussion prompt this afternoon. You'll have one on Wednesday, but I'm actually going to extend those, and I'm going to make an announcement about the due dates. Those are going to not be due until after spring break. Just because, well, actually, the Wednesday one won't be due until after spring break. Um, but with that said, I'm going to go ahead and jump right in. The stuff that we're going to do on Wednesday is a topic or subject known as stoichiometry, and it is classically a really tough one. Um, so I'm going to break Wednesday's lecture down quite a bit. I use lots of examples and models to describe that or to work through that. So I hope that it will be beneficial. And we're going to tackle it again after spring break just because of how important it is. In the meantime, though, we are going to get into the mole. I'm going to share my screen there. I'm going to open up the chat. And if you have ever heard of a mole, would you please add an M to the chat? And not the animal, I mean in the context of a chemistry class. Okay. Um, okay. So now, if we have heard of it, yes, put an M. If you have never heard of it, I'll go with a Z. That's on the opposite side of the keyboard as an M. Now, this is something that was the last thing I learned in high school chemistry before COVID hit. Yeah, so that's a that's a not a good memory, but that's a unique and significant memory. Now, and you don't have to turn your camera on for this, go ahead and raise your hand if when you learned about the mole, so you have to have learned about it, you kind of struggled to wrap your mind around it. Like I said, you don't have to turn your camera on, but I am willfully raising my hand because I struggled like heck with it. And so that's one of the reasons that we're going to spend basically the entire lecture today talking about it because it's difficult to understand. But the key thing is not that it's difficult to understand or not that it's difficult, but the key thing is that people understand it. Um, I I hear you, Charlene. I had the same sort of experience. There was for me, there was lots of jumping around, like, oh, this is 1 mole, this is more than 1 mole, and I struggled with that like crazy. Okay, sorry, I had to move my view there, and okay, good. Now, if you've ever learned about what a mole is, you probably saw something like this. And this is kind of how I was taught, hey, what's a mole? Try to get me to understand it. And the way that people classically do it is they say, hey, you know what 1 dozen is, right? You say, yeah, I know what 1 dozen is. It's 12 of something. You know, you have your example of a dozen eggs. Okay, that's 12 eggs. Okay, so that's a definition. I'm going to write this out here. This is a definition. I'll say it's a defined number. Okay. Now, for 1 mole of something is defined. Okay. So it's also a definition. But the definition is really, it's tough to wrap your mind around. The reason is because immediately when you talk about defining a mole or what is a mole, you bring this right here, this scientific notation. Now, we've already talked about scientific notation. Um, and when you look at this 10 to the 23rd, that is a positive exponent. Now, what does that 10 to the 23rd mean? That means that you're moving the decimal place. Okay. So could everyone give me a L in the chat if they follow so far? We haven't expanded this number. Give me an L if you follow and an A if I got mixed up when we transitioned from a dozen to a mole. Okay. Now we have 1 mole of something is defined, and that is defined using this number, 6.02 times 10 to the 23rd. Now, I always like to make a point to write this number out, 6.02, and I'm going to drop this decimal because what I need to do is I need to make this make sense for my number. And in order to do that, I have to move my decimal, and since it's a positive exponent, I'm going to move it. Give me an R for right or a L for left. Which direction am I going to move my decimal? Is it going this way, R, or is it going this way, L? That's right. I'm moving it to the right. So if we move this decimal 2 places, 6.02, or that is the same as 6.02 times 10 to the second. Could everyone give me a slash, forward slash or backward slash in the chat if you follow that, if you understand that scientific notation? Okay. Now, that's great. But we are taking this number, 6.02 times 10 to the 23rd. So we're not moving the decimal to the right 2 places, we're moving it 23 places. So I always like to do this kind of carefully and deliberately. So I'm going to write out 6.02, and I always have to be careful with this because um, I'm going to begin moving and I need more space. So 1, 2, and then I'm going to say 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oopsies, 2 phone. So I'm going to erase one. I erased 2 so I can put 1 back. So 23. Okay. So now I'm going to get a red dot to show this right here is the place that I'm going to, well, where I'm putting my decimal. Now, between the 2 and that decimal, I've got a lot of white space. What should I fill that white space in with? Add to the chat what I should put in there. Zeros. So I'm going to put 0, 0. And it doesn't really matter. I don't want you guys to get like focused on, okay, how many zeros do I put in? Because that's worth knowing, but it's not, I don't want you to get distracted by that. The important part here is we moved our decimal 23 places. So this number right here, now what I'm going to do is I'm going to grab this, that right there, get rid of it. Okay, and then I'm going to get rid of my decimal there. So would everyone agree, Y or N, that this is a large number? And when we kind of stress how large that number is, I think it's worthwhile to think about, well, in the English language, we use commas, or when we write um, large numbers, we use commas to denote like the thousandths place. So we do every three digits. So there's three, three. If if my number was right there, if this was, let's say that nothing else was here, okay, is this the one using E or is that different? That's a great question, Grayson. If you use the capital E on your calculator, that is the same as times 10 to the whatever power. And this symbol right here, if you're not familiar with it, it's what's known as a caret. And I know I drew an arrow pointing to something, but that's just, times 10 to the fifth. It's basically raising that five as an exponent. So if you see that on your calculator, if you see this function, you'd want to use that function instead of typing out this whole thing right here. But it effectively means the same. Okay, so if if I wrote this number out, you know, I'm putting this digit in here with a pair of commas, I think everyone would say, oh, that's 6 million. Got it. Understand that. And then if I were to, now I'm just going to erase this. And yes, this is very deliberate. I'm going to erase all this. I'm going to add some more commas. Okay, three more digits. If I put a non-zero digit right here, that'd be something billion. Okay, three more digits. A non-zero digit here, that would be trillions. A non-zero digit here, that would be quadrillions. Is everyone with me at this point where we're getting to quadrillion? Give me a one if you are, a three if you're mixed up and you lost me at some point. And all that I'm really showing here is how large this number is. So that would be a quadrillion. So then after three digits, that would be pentillion. And then this would be, I think it's sextillion. So another way of putting all of this, another way of phrasing this, I just erased those so I could write slightly cleaner commas. I'm going to write this at the top. 6.02 times 10 to the 23rd of, let's say, particles. I got to Google this real quick. Um, just so I can get the right number. Um, one pentillion, one hexillion. At some point, those very large numbers just sound like flowers. One quintillion, yeah, sextillion. Okay. So 6.02 times 10 to the 23 particles is the same as 602 sextillion particles. I think that it's helpful to say this number because I think that pretty much everyone's comfortable hearing about a million, a billion, a trillion. You get the progression. 1,000 million is the same as 1 billion. 1,000 billion is the same as 1 trillion. But then we kind of like hit the brakes a little bit because that number just becomes such a large number. Now, I'm going to erase all of this because what I want to do is ask you guys the question, does this number 6.02 times 10 to the 23rd make a little bit more sense when you see it written out in complete notation? Write that. Add a W if, yeah, that was helpful, or an I if I didn't need that, or a N if, no, it doesn't make any more sense. You've just written a very large number, and I can see that it's a very large number. Okay. Now, for those of you that this helped or you already understood it, what I really want to convey here is when you have 1 mole of something, you have a lot of that something. You have a lot of that thing. Okay. So if you had 1 mole of eggs, you'd have this many eggs. Now, what you need to be able to do, one thing that's important for you guys to be able to do is to, can't think of really a better word, but to toggle back and forth between the definition 1 mole of blank is equal to 6.02 times 10 to the 23rd of that blank. So to put some examples in there, if you had 1 mole of, let's say, cars, okay, I want you to use the same definition that I have of a car. And I'm going to draw a car for you guys. There's a car. Is that a complete car? No, because we all know that a car needs one, and then look at this. Here's depth. Two, we got, and yeah, my wheels kind of look like poorly drawn eyeballs, but there we go. Okay. One car has how many wheels? One car, and I'm talking like a sedan. Okay. So what here I'm trying to do is get you guys to recognize and kind of critically think about, okay, well, if I have a mole of something, let's think about that individual thing. What is that individual thing made up of? But before we get there, I want you to think about this statement right here. If you have 1 mole of cars, you have 6.02 times 10 to the 23rd cars. Now, chemists will say things like 1 mole carbon. And when they say this, they have 1 mole of carbon, that presents a little bit of a challenge. And that's where people say, wait a minute. Carbon, is that, they start taking a pause and they say, is carbon is that a gas? Is that a solid? But in that case, you don't need to be thinking about that, or you don't need to be thinking at that depth at that point in time. Could anyone tell me what is the individual, if you have one single carbon, you have one single carbon, fill in the blank. So I have, what's the most basic unit of carbon? Give you a hint. Starts with an A. Perfect, an atom. So when you see something like this, 1 mole of carbon, don't get mixed up on that. Instead, think, oh, okay, what's sort of implied there is 1 mole carbon atoms. Does this statement makes sense. Give me a Y or N. Okay. So that is this, from my experience, both as a student in chemistry and as a person who's taught chemistry before, this word right here, I think is one of the more important things to include when you see a statement like this. So if you have a test question or something that says, you have 3 moles of carbon, I think that it's very helpful to go ahead and say, okay, I have 3 moles of carbon atoms, because I know I'm talking about atoms there. Now, to continue that statement and to continue that, this 1 mole of carbon is equal to 1 mole of carbon atoms. And if you have 1 mole of carbon atoms, how many carbon atoms do you have? You have 6.02 times 10 to the 23rd carbon atoms. Okay. So what I've got in this black box, which I'm going to put a big star by, what I've done right here was just adding this word and stressing the importance of adding this word atoms in so that you'll understand how to kind of interpret that. Okay. But everyone give me a 1 if, okay, I follow and I understand this whole connection right here, or a 0 if, no, I'm a little mixed up on that. Okay. Seeing lots of ones. I'm happy to see that. Now, let's go back to this example of cars. Okay. 1 mole of cars. And we're going to go to this very crude definition. One car, the individual unit, essentially the atom here, has 4 wheels. Okay, so a car we can break down a little bit. You could kind of think about a car as being like a compound. It's made up of multiple things. So one car has 4 wheels. Now, if I said you have 1 mole of cars, that's a statement. And you can imagine the questions being kind of presented to you in this way. You have 1 mole of cars. Okay, statement. Great. Sweet. Awesome. The question then is how many wheels do you have? And before you answer this, oh, Grayson, great. I like that. I'm going to give you 4 different options. And I want you to add to the chat. And this is kind of a critical thinking exercise. Um, we've got option A. How many wheels do you have? And I'm looking for a precise answer. Answer A is 4 wheels. Answer B is 4 times 6.02 times 10 to the 23rd wheels. Answer C is 4 moles of wheels. And answer D is 1 mole wheels. Now, take a moment and whenever you feel ready, go ahead and answer the question in the chat. And this one's a critical thinking question because there's more than one right answer. And there are 2 kind of equally right answers. Then there are 2 answers that are not so great. I'm going to take a sip of my coffee. Just 1 second. I'll be right back. Arlo? Mommy took Walter to school. How are you doing, buddy? Hey, come here. Come here. She's good. Good. Right here. Sorry, buddy.
What can I eat them? It's like
I need to get you a remote.
a lot of fun. That's good. Oh, really? I want to play this now. Sure. No,
No, really go finish my class first. Okay, everyone. Sorry about that. Um, okay. I'm guessing. Feel like it's a trick question. Is it a dog or a baby? I'm guessing baby. It's B and C, same thing. This was one of my kids. Um, he's like been week and a half. It's like sick and then he's not sick. Okay, so I'm seeing some answers though. B and C. If you marked B or C, you're equally correct. Okay, so now let's go through. Thanks. Let's work through all these different answer options. Question or answer option A, four wheels. Well, I'm sure that somebody was like, well, you if you have a million of something, you have four of something. But this wasn't really what I was going for. I was going for a precise answer. And the same thing goes for answer option D, because that's not the total. I was looking for the total here. So A and D are out. B and C are equally correct though, because let's think about this number. If you have 6.02 times 10 to the 23rd, in just a little bit, times 10 to the 23rd of wheels, you have 1 mole wheels. So then I wouldn't give you these two options on the exam or quiz or anything like that, but these two, B and C, are equally correct. So whenever I am kind of presenting to you the idea of, just a second. No, I don't want to save the file.
I don't know.
So, so I want you to be able to convert between 1 mole of something is equal to 6.02 times 10 to the 23rd of something. And I want you to look at this as a two-way road. So you can, if I give you a definition like, hey, you have this many moles of something, how many quantify how many of that thing there are. So just like you would say, I have 4 dozen eggs, you would be able to interpret that and convert that and say, okay, well, you have 48 eggs. If somebody said, well, I've got 72 eggs, you could say, okay, well, that's the same as 6 dozen eggs. Can you give me a J in the chat if that makes sense? Or a 6 in the chat if that's confusing. And actually, a six in the chat if I don't get it, because I think that it's possible to answer this sort of question and go back and forth between these, but it still be confusing. Okay. So this is great. Now, what I'm going to do is if you understand this right here, this is like, this is where I want you to be right now. And we're going to build from this because we're going to define, kind of establish and get some more definitions working in here to piece together like a more complete story. So this is a, hey, what does a mole look like? Well, people celebrate and have fun with Mole Day on October 23rd, 10/23. Now, what does a mole look like? Do these one mole samples, first of all, do they have the same mass? And what we've got here, just so you guys know, this right here is 1 mole of copper wire. This right here is 1 mole of iron. This is 1 mole of sulfur, 1 mole of mercury, and 1 mole of helium gas. Now, I think all of you can look at this and say, okay, well, solid. And you could give other descriptions like physical property descriptions. Well, it's kind of reddish, um, solid, and that's a blackish gray solid. Not only is it a solid and it's blackish gray, but also it looks like it's kind of granular. So even these two descriptions of these both being solid, well, they're kind of incompatible or different solids from one another. Now, this next one, sulfur, that is a solid. And if you were to like imagine that iron, if you picked up this iron, I like to imagine that it would kind of feel like grains of sand, hence why it's granular. When I look at the iron, I think about that, or the copper, I think like, oh man, I don't want to cut my finger. Um, this is similar to a pound of feathers versus a pound of bricks. I like that. Um, when you look at the sulfur, I always kind of envision this as being like a very brittle piece of chalk. Like if you had enough force in your fingers, and it wouldn't take a huge amount, but you could squeeze it and it would turn into a powder very easily. This last one, mercury, I I know that I don't know if anyone has this experience, but I remember the first time I mentioned chemistry to like my aunt and uncle or my grandparents or something. They were like, "Oh, you guys do anything with mercury?" And apparently back in the 1960s and before, it was pretty commonplace to play with, maybe not play with, but have mercury as a part of a laboratory experiment. Now we don't do that because mercury is pretty highly carcinogenic, so it can cause cancer. So you try to err away from that. But mercury here, notice how that's in a beaker. The reason for that is because at room temperature, this is a liquid. So it's a liquid, but and then last but not least is helium. All of these samples, they have differences. But all of these samples, these are all 1 mole samples. Now, if you look at the helium, well, if you pop that balloon, that helium gas is just going to go everywhere. If you were to spill the mercury, it's going to stay in a small space. So there's differences, even though these are all 1 mole samples. So if you looked at this helium, and I were to ask you how many atoms are in this balloon, you'd say, well, there's 6.02 times 10 to the 23rd helium atoms. Okay, now let's look at this copper wire. Well, how many atoms make up that copper wire? 6.02 times 10 to the 23rd atoms make up that copper wire. Same thing for the iron, same thing for the sulfur, and same thing for the mercury. Now, that's the number of atoms. Could you, if you look at the iron and you're like, oh, well, I can, get a hammer and pulverize it even more. Yeah, you could, but you're never going to break it up all the way to the number of atoms. But what I want you to see is that these are all 1 mole samples. They occupy different spaces. They're going to feel different. They're going to exist in the world different from one another. Now, the question though here is they have the same mass. I mean, the helium, if you subtract it, like, could you get the mass of this? Yeah, get the mass of the balloon, and then you'd be able to deduce, okay, well, what's the mass of the balloon alone? And then what's the mass of the balloon when it's filled up? And you could deduce the mass of the gas in that balloon. Now, if you ever want to know the masses of these, which, spoiler alert, you'll need to know these and not have them memorized or anything like that, but you'll need to know these masses. There's one good place that you can look. That's the periodic table. So if we look, let's say at the sulfur, for example, 32.07, we talked about that number. That's the average AVG weighted mass of sulfur. So what that means, or average isotopic mass. So if you got, well, if you got the all these different isotopes and figured out their masses, then you could figure out that the average mass of an atom of, so one atom of sulfur, and I'm going to go ahead and say, I'm going to change this. The average atom of sulfur has a mass of 32.07. Now, I mentioned this previously, but it's particularly important here. The units for this are AMU. Okay. So this is a true statement. These units are important. Now, how does this number, this 32.07, relate to a mole of a mass? Well, 1 mole of sulfur, and we see it down here, it kind of looks like popcorn. It's not popcorn. 1 mole of sulfur is 32.07 grams. Now, 1 mole of sulfur, what's the word that is helpful to include right here? Add it to the chat if you remember the word that might be a little bit more defining. And it's not powder, but think about what we break or what we can break sulfur down all the way to. What's the individual units of sulfur? Atoms. So it's helpful to say 1 mole of sulfur atoms is 32.07 grams. So when you look at this plate right here, or this petri dish, well, that has a mass of 32.1. And just so you guys know, if you look at this digital balance here, this one's not going to go more than 1 digit, 1 decimal place. So this one, it has to round up. So that's why we arrive at 32.1. But on this plate, there's approximately 6.02 times 10 to the 23rd sulfur atoms. Could everyone give me a Y or N if that makes sense? Okay, awesome. Now, I want to do just one minor detour with respect to this. I'm going to grab this part of the slide. And what I always like to do is kind of give myself, the simpler that I can make a question for me, the easier it is for me to understand. So what I'm going to give you is a hypothetical situation. You have, let's say, 32 grams of aluminum. And I'm going to go ahead and add the word atoms, just so there's no confusion there. I have 32 grams of atoms. And I want to relate that mass to numbers of moles. So I'm going to say these three statements. I have less than 1 mole of aluminum atoms. I have exactly 1 mole of aluminum atoms. And finally, I have more than 1 mole of aluminum atoms. Cameron's on it. You're absolutely right. So this 32 grams, we want to relate that to our symbol on the periodic table. 13 doesn't have anything to do with the mass of 1 mole, but what we want to do is we want to look at the 26.981. Okay, I got a private message. More. 1 mole should be just absolutely. Great job, John. Yeah. So what we're doing is we're just essentially we're asking this question of is 32G greater than, equal to, or less than? And I'm going to use those symbols, but I could also say more than, equal, or less than 26.9. That's going to be my reference number. And as soon as you kind of distill it down to that, then you can say, well, I know that 32 is more than 26. So since 26.981538 is the definition for 1 mole, I can say, well, I have, it's not less than, it's not exactly, it's going to be more than. Could everyone give me a 3 in the chat if I follow that sort of question, I follow that sort of logic, or an 8 if I got a little bit mixed up? Okay. I think that it's really helpful to do that sort of thing because we have these different definitions and we're trying to relate 1 mole to 6.02, or I'll say 1 mole of atoms to 6.02 times 10 to the 23rd atoms. And then we're relating 1 mole of atoms also to, well, a mass. I'm going to say mass on periodic table. So if you remember a moment ago when I gave you this kind of scenario, I said, I want you to be able to go, let's see, I'm going to go ahead and just grab it from, yeah, this right here. This idea. 1 mole of something is equal to 6.02 times 10 to the 23rd of something. We're going to expand on that, and it's at the bottom here. But I want to kind of show you that it's a little bit more complicated because what we're really doing is saying 1 mole, and we're connecting that to um, number of atoms. And we're doing that with the help of this 6.02 times 10 to the 23rd, which you will sometimes see referred to as Avogadro's number. Not to be mistaken with avocado's number, which is, without a doubt, everyone's favorite number because avocados are fantastic. But we're also drawing a connection between number of moles and what's known as the molar mass, which is on the periodic table, on P table. Okay. But then to add a little bit more complexity to it, if I tell you I have 26.981538 grams of aluminum atoms. I think that everyone would feel comfortable saying, well, I have 1 mole of Al atoms. Give me a 9 in the chat if you agree with that statement and you understand that. Well, another way to phrase this is to say, I have 6.02 times 10 to the 23rd Al atoms. Or sorry, yeah, that's right. Give me a 4 in the chat if you understand this second statement here. All of this is true because if you have this precise amount, well, that's kind of our defined mass of 1 mole. Okay, so that makes this statement true. Well, if you have 1 mole of something, then you have 6.02 times 10 to the 23rd of that something. So it's going to add kind of another layer or another kind of arrow. So this is how I kind of want you to think about relationships between numbers of atoms, molar mass, and what a mole is. If you can do that, that's going to put you in a very good position. Now, if we were to look at this question, I think that would grab this. I can't remember if I cropped this or not. Yeah, good. Okay, so there's hidden information. Nope, never mind. Um, so if we look at this again, which 1 mole sample has the greatest mass? Well, this right here, if I put this on a digital balance, it'd be 63.55 grams. Could anyone add to the chat what would the mass of mercury be? I'm going to get the sulfur. That would be approximately 32.07. You might have to go to the periodic table or ptable.com. I'm going to circle these just because I'm circling that as a pattern. 32.07 grams. Now I'll grab the mass of the helium. The mass of the helium is 4.0026 grams. Then I'll grab the mercury, which is 200.59 grams. And last but not least is the iron, 55.845 grams. Okay. So my first question is, does everyone understand that these numbers that I wrote on the table or on the slide are coming from the periodic table? Give me a Y or an N to that. And that's exactly where you'll reference them from. That's exactly what will be on your exam. So that's where that information is going to come from. So this sort of question, well, which 1 mole sample has the greatest mass? This is really just it, you know, it doesn't matter what represents it. It doesn't matter the diagram here. This is, I think, a helpful view of it. But it's not really intended to be a game changer. Instead, these numbers, you're just going to look at the periodic table and you're going to say, oh, okay, well, mercury has a mass of 200.59. So E, mercury is the correct answer. Now, the next level of complexity to this is, well, what if you have a compound? Well, just like we talked about a car, well, one car is made up of a car body and 4 wheels. If you have 1 mole of cars, you have 4 times that many wheels. Now, if we're calculating the molar mass of a compound, what do? Carbon dioxide is 1C plus O plus O. So if I have 1 mole of CO2, that means, and we're not quite to mass, so I'm not ready for that number yet, but I want you to understand, well, if you have 1 mole of CO2, that is equal to 1 mole of C plus, what else should I add that to? I gotta account for, could anyone add to the chat what needs to be written in this space right here? CO2 consists of carbon and oxygen, right? I got a private message that is correct. 2 moles of O. Why 2 moles of O? Okay, well let's look at what carbon dioxide looks like. It looks like this. If I have 6.02 times 10 to the 23rd of this, that whole thing, I've got 6.02 times 10 to the 23rd oxygens, and then, well, 6.02 times 10 to the 23rd oxygens. If I have 1 mole of CO2, that means I have all of the things that make up that CO2. 1 mole of CO2 molecules. What are the parts that build up the number of molecules? Well, there's 1 mole of carbon, 2 moles of oxygen. So does this right here, does this breakdown make sense? Give me a 7 if yes, and a 3 if no, it does not make any sense. Okay. Now, this question can also be asked in one slightly more, I feel comfortable calling this a tricky way of asking it. You have 4 moles of CH4. And I'll go ahead and add the word that I like to add here, CH4 molecules. Okay. Now, my question is, how many moles of atoms do you have? And here's where I'm going to ask you to take a pause. Whenever you look at this question, the part that's the critical part of the question, how many moles of atoms? Um, Give me a Y or an N. Am I specifying carbon atoms? No. Am I specifying hydrogen atoms? No, I'm not. I'm speaking generally. So if you have 4 moles of CH4 molecules, you could think about it as 4 whole things. How many total things do you have? And put it in terms of moles. You don't have to use or your hint is you don't have to use 6.02 times 10 to the 23rd to answer this question. Okay, I got CH4 times 4. How many atoms? Take a minute and answer this one. And, I'm going to go ahead and do this and use this idea to kind of drive your thinking. If you have 1 mole of CH4, or actually, no, not 1 mole. If you have one molecule of CH4, how many atoms do you have? You've just got one of that thing, one CH4. 5. John, you're absolutely right. Okay. And the answer to this one is also 5. So I'm going to give myself another slide to break this one down a little bit. One molecule, CH4. Maya, you're absolutely right. One molecule CH4 means you've got 1 carbon, 4 hydrogens. And if I'm asking how many atoms? Well, one carbon atom, four hydrogen atoms. That leads to five atoms. Now, if I pivot a little bit, and if I say 1 mole of CH4 molecules, well, then if you have 1 mole of something, you have 6.02 times 10 to the 23rd, but you also have that definition that you can lean back on. So 1 mole. So this would be, rather than five atoms, it'd be 5 moles of atoms. Okay. On a scale of one being, oh, I got that. It took me a minute, but I got it. And three being, that's tough to wrap my mind around, but I think I'm going to get there. It's just going to take a minute because I got a lot of definitions that you've thrown at me. And that was a lengthy response for three. Okay. Two. Okay. So when you see these sorts of questions, just be careful and think about what's the individual unit that we're talking about and what is that composed of. The example that I very regularly fall back on or revert to is the example of the car. I have one car. Okay. If I have one car, then I've got four wheels. Okay. What else do I have if I have one car? I've got, possibly two captain seats or a bench. I don't know. Just think about the example of a car and then try to expand upon that. Okay. Now we'll do some examples and then we're going to call it a day. So this right here, 1.8 grams of H2O and 8.0 grams of Br2. So the question here that you could be able to answer is how many moles are in each of these? Okay. 1.8 grams of H2O. Well, how many moles? How do we do this? Well, there's a way that this can be done that basically gives you a conversion, or you have a conversion. You have to convert number of grams of H2O to number of moles H2O. Okay. So if we look at the periodic table, what we will see is that the molar mass of H2O is, well, two hydrogens collectively have a mass of 2. So 1 plus 1 is 2. Oxygen has a mass of 16. So we're looking at 18 grams. So 18 grams of H2O is 1 mole H2O. Now, I'm going to jump over here to Br2. Well, this is 160 grams of Br2 is 1 mole Br2. Because each mole of bromine, of Br, has a mass of 80. So 80 plus 80, that's where we get 160. So now the question is, how many moles of each do we have? We want to take this mass and convert it to moles. How do we do that? Well, we do that with this right here as our conversion factor. So to set this up, has anyone ever heard of dimensional analysis? Maybe you have, you probably have, you possibly have. Just a second, bud. And you look at it, some people refer to it as the picket fence method. And our dimensional analysis is going to be set up like this. Basically, it's a horizontal line, a vertical line, and then an equal sign. Now, in this position right here, you're going to start by putting the number that you are given. And then I'm going to go in yellow. What is in yellow is going to be your conversion factor. And then last but not least, what I'm going to put a red, no, I'll go with a black box around right here. That right there is going to be what units you want. So starting number, I'll put this whole thing as conversion factor. Conversion factor. And then in the black box, units you want. Okay. If you've ever seen dimensional analysis before and it has not been an issue for you, fantastic. If you've got it down, great. If this is new to you, then I think that getting all of this right here is going to be very helpful. And remembering that what's in the numerator right here is what you want. So what we're going to do is we're going to take this number, our starting point. I'm going to use the same red lines. Our starting number is that 1.8 grams of H2O. Then I'm going to put a check mark here, and I'm going to put check mark by that number. Then we've got to go to our conversion factor. Now, I said previously, this is our conversion factor. But with this as our conversion factor, we've got to know, well, how do we equate this? How do we take this and put it into here? And the answer to that is we want to put units, the units that we started with right here, the grams of H2O, we want those in the denominator. Because what happens if you have something in the numerator and the denominator? Add that to the chat. What happens to that? You're right. They will cancel out. So that means what we want to do is we want to take this conversion factor and we want to put the 18 grams of H2O on the bottom. And then on top, we want to put 1 mole H2O. And go back to a red pen. Grams of H2O will cancel. Grams of H2O will cancel. So now we've canceled the units, and all that we care about are the numbers. So we're going to multiply everything on top, all those numbers that are on the top, and divide by what's on the bottom. So 1.8 times 1 is 1.8. 1.8 divided by 18 is going to be 0.1. So our answer is 0.1 mole H2O. Now, one thing that you'll probably see is when people talk about moles, they will commonly save themselves the stress and the time of writing MOLE and they'll write MOL. So, they don't have to write E or ES. Okay, so now let's go over to this one right here. Let's do the same operation. Horizontal line, vertical line, equal sign. What number are we starting with? 8.0. And I'm going to write grams of Br2. Then what goes down here? Add to the chat what goes down there. That's right, 160 grams of Br2. What goes on top is 1 mole Br2. And then that gets us, well, 8 times 1 is 8. 8 divided by 160 is 0.05 moles. And here I'm writing MOLES, and that's fine. Br2. So effectively, if you say, hey, I have 8 grams of Br2, that's the same as saying I have 0.5 moles of Br2. So now if we were to go back just a second and look at that triangle again. What we did was we took a mass input, related it to our molar mass. We kind of went, this was our workflow right there. That's what we were aiming to do. Okay. Could everyone give me a 5 if they think, I think I'm getting the hang of this, or a V if I'm struggling with it, but I think I will get the hang of it. Okay. Okay, great. So one of the things that it might seem pretty trivial. It might seem like, well, that's kind of excessive. Whenever I'm writing this right here, grams, 8.0 grams of BR2, I find that I make fewer mistakes when I write this, grams of BR2, because then I write it here. Because then I can come back and say, oh, okay, well, yeah, those units canceled. Those units canceled. I'm good. Um, I remember whenever I took my first chemistry class, I would skip that. I would write 8 over 160. And then I would just end up like the answers that I would get would be backwards because basically I skipped a step there. So I strongly recommend writing your units down. This right here is the same sort of sample or the same sort of example. But what are we doing differently? We're going from moles to mass. So in this case, what this is showing us is we have 0.1 moles of CuSO4 and 1.1 mole of K2Cr2O7. So this question is basically, it's not a question that's presented here, but essentially this is asking what mass of each of these do you have? So essentially what you've got is, again, I'm going to go back to, I'm going to just grab this from the previous slide. Copy this, and I'll just add this in. Same setup, but the numbers are a little bit different. In this case, I'm going to use the same red pen, horizontal line, vertical line. What's our starting number? Well, that is 0.1 mole CuSO4. Okay. Now, we have our conversion factor, which we see on the periodic table. We have to construct our conversion factor. So what I'm going to say is 1 mole CuSO4 is equal to, what's the mole of copper, or 1 mole of copper is 63.55 plus S, which is 32. It's 32.1, I'll say, plus, if you look at the periodic table, you see oxygen is 15.999999. I'm going to round that up. I'm going to round that up to 16, and then I'm going to say plus 4 times 16. So I'll say 63.55 plus 32.1 plus 64. Whenever I add all those up, 63.55 plus 32.1 plus 64 gives me 159.65. Okay, so here's my conversion factor. And I just did the thing that I said is a bad idea. Grams CuSO4. I forgot to write that. So this is my conversion factor. Give me an A or B. What goes on bottom? Is it 1 mole CuSO4 or is it 159.65? What goes on bottom? Well, remember, I want to take my moles of CuSO4. So A is the correct answer. That would be this right here. So 1 mole CuSO4. because what I want, my question is asking what mass do I have? My mass is my molar mass that's going to go on top, which is the 159.65 grams of CuSO4. Gotta extend that on a little bit. Okay. So now my answer to this is 0.1 times 159.65. Well, whenever I do that, I plug it into the calculator, I end up with 15.965 grams of CuSO4. Okay, so I'm going to ask you guys and give me a response in the chat. What was the trickiest part of this? Was it one, the identifying ID, the starting number? Two, calculating the conversion factor? Or three, organizing what goes where? Okay, so I know not everyone has responded, but from the quick number or quick responses that I've gotten, it seems like this organizing what goes where was one of the more common issues. I've gotten a handful of private messages. Um, and the good thing about this is that one, we're going to do one more example before we call it a day. Two, when you are doing this sort of problem, I think that it's super helpful to break it down as much as possible and say, hey, this right here, what does this consist of? This consists of knowing this. Okay, so that's one thing. Do I know the organization of it? Do I know that I put my starting number in this location? And then next to that, I have my conversion factor. As soon as you establish that and feel good about that and organize that, then you can go on to look at these other things and say, oh, okay, well, my issue is calculating the conversion factor. Okay. How do you do that? Well, how do you calculate the conversion factor is you look at the formula, K2Cr2O7. Okay. So what I'm going to do in order to calculate this conversion factor is I'm going to say 1 mole of K2Cr2O7 is equal to, and I've got a periodic table on my other screen, so that's why I'm looking over here. If I look on the periodic table, that's what I'm looking for. So K2, okay. K on the periodic table is 39.098. I'm going to round that to 39.1. So I've got 2 times 39.1 plus CR, which is 51.996. I'm going to round that to 52. So I'm going to say 2 times 52. And if you're looking at this and you're like, how do I know when to round or not round? I wouldn't lose any sleep over that because that's not going to separate correct answers from incorrect answers. And then the last one is 7 times oxygen's mass, which is 16. So 7 times 16 is going to be 112 or 7 times 16. So now we're looking at 2 times 39, which is 78.2. 78.2 plus 2 times 52, which is 104, plus 7 times 16, which I previously said was 112. Got those numbers. Now, I'm not going to try mental math on this one. 78.2 plus 104 plus 112. 294.2 grams of K2 Cr2O7. So that's adding up those masses, and there we go. So there's our conversion factor. So now we'll go back to setting this all up. Now, what is our starting number? It all depends on the question and how it's asked. But this question, you should expect to see what is the mass of 0.1 moles of K2Cr2O7. So I'm going to write that as my starting number. 0.1 moles K2Cr2O7. Okay, so that's the starting point. Now, that's the first phase, basically, of my dimensional analysis. The next phase is dealing with my conversion factor. What is my conversion factor? My conversion factor is this right here. Okay, so I've calculated my conversion factor. I've placed my starting material or starting number. And now what I need to do is organize my conversion factor. Well, what are the units that I have for my starting material or my starting number? That would be moles of K2Cr2O7. So in this case, 1 mole of K2Cr2O7. That's in the numerator and the denominator, so they will cancel out. And then my mass is going to go above that, and that would be the 294.2 grams of K2Cr2O7. As soon as we get that, then it's 0.1 times 294 divided by 1, and we're good. Divided by 1 is the same number. So 0.1 times 294.2, plug that into your calculator, you get 29.42 grams of K2Cr2O7. So if this question was asking you, well, what's the mass of each one of these and which one of these has the greater mass? Is it zero point 0.1 mole of CuSO4 or is it zero point 0.1 mole of K2Cr2O7? Your answer would be the, well, 0.1 moles of K2Cr2O7. All right, that's what I got. And that's where we're going to end today. Like I said earlier, Wednesday's lecture will be pre-recorded. I will post that on Canvas. I'll have office hours on Wednesday and a little bit more availability, but I just wanted to give Wednesday as kind of like a flex day for you. Um, if I don't see an office hours either today or Wednesday, I hope you enjoy your break. Take some time to relax, be safe, and have a great rest of your week. Good luck on your exam for the rest of the week. So we don't meet with the same Zoom link on Wednesday. Correct. Everything will be pre-recorded. If you want to meet, same office hours. But have a great, yeah, thank you very much. And hope you, thank you. Sorry, I just mean good luck on any other exams that you might have, because other classes and stuff. That's all. You don't have an exam for my class. Sorry about that. I know you guys probably have papers and stuff due, maybe projects before spring break, but sorry. All right, see y'all. Stop my share and then